Okay, assalamualaikum, a very good afternoon or morning perhaps. Okay, now let's continue on the second part or part B of the second chapter, which is on the equilibrium. So let's go. Okay, here is the outline lah for part B. So we will look into the continuation of the distribution coefficient. Okay, the effect of the ionic strength on the solubility of salts lah. Okay, what is the ionic strength, the effect of ionic strength, ion charge and the ion size of the activity coefficient, chemical equilibrium and electronic effects. Then after that we will look into thermodynamic inspiration. Okay, under that we have multiple kind of law, including the Gibbs free energy, Clausius-Clapeyron equation, Trotter's and also the Roth's law. Okay, so they have different rule lah, depends the kind of what kind of condition, okay, of the analysis that you need to do. Okay, then you need to follow certain rules based on their law lah. Okay, so kita akan sambung sedikit. Okay, at the last previous slide, okay, before we end our session last week, okay, so we it has been told to you guys that the distribution coefficient involve, okay, both the ionized and also the neutral compound lah, neutral compound. So the application of distribution coefficient focus on the species of chemical which is can be ionized and also can be neutral. Okay, for example, drugs. Okay, drugs when we consume it can be ionized. Okay, so if you look over here, this is example of one of the drug lah, ibuprofen, has the typical of log DH profile that is characteristic of acidic compound. Okay, so if you look over here, that the ibuprofen, okay, it's look that it's stable at pH lower than 4. So at pH lower than 4, okay, at pH lower than 4 is mean that it's stable. Okay, so at pH lower than 4 is stable, it's keep being natural. Okay, so what happen if the pH is more than 4? So if you look over here, the graph starting become unstable, going down. Okay, the log D, okay, it means that some dissociation of a proton occur, some deprotonated of process of deprotonation of proton occur. So it will lose one of its proton over there, so deprotonated, and then it become charged, right? So when it become charged, if you look over here at high pH, the carboxylic group reach the fully ionized state, then and hydrophilicity become enhanced. Okay, so if you look over here, if we do understand the concept of ionization, okay, the ionized compound is actually more hydrophilic, they are water lover, right? Same goes to the ibuprofen over here. Okay, so if you want to have a drug that good for human lah, okay, inside our body, they want to be absorbed. Okay, so we know that in our body, okay, in our body is kind of acidic. Okay, you need them to absorb very well inside of your body system, right? Including your tissue fat, your brain, composed of a lot of fat. So you need to what we call produce the drug, which is kind of the acidic drug. Okay, here is the example lah. So they become neutral, because if the drug is water soluble, it will most likely, okay, akan keluar melalui air kencing lah. Okay, that is typical example that I can give to you lah. So this is the example. Okay, I hope you guys still remember about pKa, whatever the pH, how they relate the ionization process. I don't think I need to describe into that detail lah. Okay, so what we need to understand that, okay, distribution coefficient, it involve both the ionized and also the unionized. Okay, so if myself, okay, want to calculate the KD, as we know that KD involve the K, okay, the concentration A, okay, K A in the what we call desired phase lah, the desired phase, the first phase, or you can call the desired phase or the initial phase. Okay, so you need to calculate both, okay, the plus one and also plus the neutral one lah. Same goes to the below, right? So that's the thing that you need to do. Okay, and then you need to understand how to read the graph. Okay, you need to understand, okay, at pH is stable. Okay, at pH start to ionize. Okay, right, let's say for example the situation that we give you the basic drug. Okay, the basic drug. Okay, for example like this. So we need to understand that here is stable. After it reach this pH, start to deprotonated. Okay, so my suggestion lah to make your life do not harder lah. That's usually we as analysts, okay, we want to make sure that everything is neutral, so you don't need to calculate both of the unionized and also ionized. Okay, so what you can do that you adjust back the pH, okay, so that they can be neutral, and then you can just use the partition coefficient lah, or you can just use the Kp. Okay, then you can calculate lah based on the concentration that you found. So that is the easiest one that you can do lah. Okay, right. Okay, here is the distribution coefficient of Kd, how to calculate them. Okay, right, if you look over here, Kd, the way of the calculation is not much different to partition coefficient. Okay, where you need to calculate the concentration of A in the phase 1 and concentration of A in the phase 2 lah. So I usually love to use the desired phase or also the initial phase lah. Okay, initial phase, because why? Okay, in liquid extraction lah. Okay, in liquid extraction, okay, so it's not necessarily that your desired phase is at above, usually at above. Sometimes it can be at the bottom, right? It can be at the bottom. Let's say you use the typical liquid extraction, okay, using this particular apparatus. I'm not really remember where is it, funnel something. Okay, so it's not necessarily that this one, okay, will be your phase of interest. It can be here, it can be here as well. So that's why I love to use phase. It means that when you try to extract, the first phase here refer to the extractant solvent lah, the desired phase. Mean that you want your analyte to be here, for example, or you want your analyte to be here. That's why I'm always using desired phase. So if you look over here, it's about the same, but it's a little bit different. Okay, so let's say for example here, in the Kp, the equation, okay, can be replaced by activity lah. Activity is including, okay, if you look over here, alpha refer to activity, and then alpha is actually equal to a concentration of your compound of interest, okay, in the desired phase multiplied by activity coefficient. Okay, right. So if you look over here, same goes to the initial phase. Okay, we need to multiply the concentration with the activity coefficient. Okay, it's a little bit complicated, right? Okay, that's why myself, okay, if I'm as the chemist, I will go, I don't want to we call headache my head with all the activity coefficient and so far and so on. So I will try my best to remove, not remove lah, I will try my best to make sure that all analyte is unionized. Then I will do the extraction process, so it will not disturb my calculation after on. But if it's necessary, nothing can do lah, so you need to understand. So if you look over here, that the distribution coefficient is affected at high ionic strength. If at low ionic strength, the total concentration is mean that at the low ionic strength lah, the activity coefficient approach unity, so here approach to 1, so you can just ignore that. And then you can just focus on the concentration of your desired compound in the initial in the desired phase, and also the concentration of your the remaining compound in the initial phase, right? So equal to Kp lah, Kp. Okay, right. So here is the effect of ionic strength on solubility of salts lah. Okay, selalunya lah kita guna distribution coefficient ni lebih kepada salt ataupun drugs lah. Kita akan cuba faham kat sini based on solubility of salts. Okay, later on you akan belajar tentang common ion effect dengan non-common ion effect. Tapi sebelum tu kita nak faham kenapa on certain situation bila kita tambah the strengthen of the ionic activity, it will affect the solubility. Okay, kita akan belajar tu dulu. Apa kaitannya kan? Okay, apa kaitannya? So why does the solubility increase when salts are added to solution? Kenapa solubility to increase when we tambah salt tu? Contohnya lah dekat sini saya bagi contohnya AgCl lah. Sini AgCl. Okay, alamak. I should change to pointer option to pen. Okay, so AgCl. If you increase the ionic strength, okay, if you increase the ionic strength of the solution by adding salts, it will increase the the radius, okay, ionic atmosphere lah. So I believe it is called, tak dekat sini maklumat tu, hydrated ion lah. The ion is become hydrated. What is mean by hydrated? It mean that, for example, you increase the ionic strength of the solution, okay, the ion will get hydrated. It mean that the molecular compound of water, they will start to berkumpul lah. Okay, so not really become a bond, but they berkumpul kat sini. Okay, so what happened that as it's become larger, the hydrated punya area lah, hydrated ion, we call that the hydrated ion, the ionic atmosphere become larger, so it will reduce the interaction between both these both particular species of chemical. Okay, so that's why bila kita tambah ionic strength of the solution, okay, dia akan lagi tend to dissociate. Okay, itu kalau kata non-common ion effect lah. Okay, non-common ion effect. Okay, so kalau kita tengok kat sini lah, contohnya kat sini potassium hydrogen tartrate solubility lah. I'm not really sure, K something something lah, K something something compound. Okay, so if you look over here, KCl is the common ion effect. Okay, common ion effect. Okay, meanwhile the magnesium sulfate is non-common ion effect. Okay, apa perbezaan common ion effect dengan non-common ion effect? Okay, common ion effect bila kita tambah salt dalam solution tu adalah dengan hasrat kita nak reduce the solubility. Contohnya lah, kalau kata kita nak trap certain toxic sebelum, contohnya kita macam nak filter air, kita nak filter air bersih, tapi kita tak nak ada compound daripada maksudnya takungan yang asal kita nak bersihkan air tu terlepas keluar daripada that particular membrane atau filtration system. Apa yang kita boleh buat, kita boleh tambah common ion untuk kita jadikan that particular contamination ataupun particular yang compound kita tak nak lepas daripada filter tu dengan kita tambahkan common ion effect. So common ion effect ni apa dia? Common ion effect ni bila kita tambah the similar species of chemical lah. Contohnya macam ni, kita potassium hydrated tartrate solubility, bila kita tambah KCl, they have similar ion. Okay, they have similar ion, so it will somehow reduce the ionic strength lah. Okay, reduce the ionic strength, so the atmosphere become not that big. Water molecule dia tak nak berkumpul terlalu rapat, so atmosphere become reduced, smaller, and then they tend to bond together, so it will not get dissociate much lah. So dia akan terkumpul, the reduce is the potential of solubility. Tapi seandainya lah, kalau contohnya okay, you buat filtration ataupun you buat membrane, lepas tu you nak extract certain compound yang you rasa benefit, dan you nak tambah that particular solubility of that particular compound, what you can do, introduce non-common ion effect. Contohnya macam sini, bila you tambah magnesium sulfate, there is no common ion effect. It will increase the ionic strength and then it will increase the solubility. Okay, is how actually I explain this one lah. Okay, right. Kalau tak faham nanti boleh tanyalah buat discussion. Okay. Okay, now in the next process, we know that already. Okay, we know that already at low ionic strength, the activity not that much. We can cancel them out. Okay, from the equation. Okay, so but we need to know what is ionic strength. Okay, how you can calculate them. Ionic strength is measure of the total concentration of ions in the solution lah. So is this the formula 1/2 multiplied by the sum of ion, okay, concentration, and should put bracket over here lah. So bracket should put bracket over here, should bracket over here lah. Okay, so this is how you can do it. Okay, alright. So if you look over here, C denoted for the concentration of the ion. Okay, but you need to calculate the actual ratio of concentration over 1 molar. Z is the charge of each individual ion. For example, NaCl, the individual ion is Na plus Cl minus. Charge is 1 lah. Dan kan kalau you guna contohnya hydrogen sulfate, H2SO4, right? It's supposed to be H plus SO4 2 minus. So it will be 2, here will be 1 lah. Okay, that is different story. Right now the example is only using the HCl. So if for example the question asks you find the ionic strength of 0.1 molar sodium chloride solution, so this how you calculate them. Okay, half, okay, then you multiple by, okay, in this particular total bracket, 0.1 molar over 1 molar multiple by plus its own charge, okay, square, okay, square, and then here 0.1 molar divided by 1 molar and multiple by its own charge. Okay, so you get about 0.1. That is for in terms of the ionic strength, how you can determine them. Okay, so now let's look on the effect of the ionic strength, ion charge, and ion size or activity coefficient. Okay, here is the, I just give you the example lah. I don't think that I will ask you to calculate this because it's kind of complicated. I think you guys, I'm not really sure if you guys already done this during the physical chemistry. I'm not really sure about that. So I just want you guys make sure that you guys understand. Okay, the equation Z is referred to charge, okay, of the compound, right, or the ion that you want to analyze. U, okay, for example, U is the ionic strength lah. So ionic strength, okay. So alpha is the diameter lah, the diameter of hydrated ion. Hydrated ion is like, for example, I already told you that it's surrounding by the molecular ion, okay, up to the certain, the atmosphere, okay, this diameter, right. If you look over here, the ion size alpha blah 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 provide good agreement between measured activity and coefficient. Alpha is diameter of hydrated ion. As ionic strength increase, the activity coefficient decrease. The activity coefficient approach unity as the ionic strength approach 0. Okay, if you look over here, log Y kan, log Y, I'm not sure how to call this. I call it as log Y. Kalau tak percaya, you boleh try kira Kalau log Y, kalau you kira shift log lah. Kalau kata shift log 0.00Y compare dengan 0.1. Okay, kalau kata ionic strength to decrease, okay, ionic strength tak banyak kan, ionic strength tak banyak, it mean that kalau you darab kat atas ni pun you akan dapat 0.000 something. And then bila you try shift log calculation kan, shift log tak silap saya kalau dalam calculator tu IO lah, IO contohnya 0.01, you will try, okay, you akan dapat jawapan close to 1, okay, close to 1. Tapi seandainya ionic strength is great, okay, ionic strength tinggi, okay, you akan dapat more than, okay, more than 1 lah. Okay, contohnya IO1, for example, you boleh kira nanti akan jadi beratus-ratus beribu-ribu lah, if I'm not mistaken lah. Try lah, saya pun tak ingat sangat. Okay, so you will try. So based on this equation alone, saya nak tunjuk kat sini yang pentingnya adalah kalau kata ionic strength to increase, okay, ionic strength to increase, okay, kita kena kira, okay, tapi kalau ionic strength tu tak banyak, okay, ionic strength tu tak banyak, berkurang, kita punya aktiviti tu akan approach unity, maksudnya dekat dengan satu lah. So it can be cancelled out, we can just calculate directly based on the concentration only. Okay, so if you look over here, the smaller, the another factor is the smaller the ion size, the more important activity effects become. Kalau kita tengok sini based on equation ni, kalau kata lagi kecil lah, lagilah macam tak ada, not sorry, kalau kata lagi kecil maksudnya lagi important lah activity tu. Maksudnya kita kena kira lah that particular activity. Kalau kata ion size kita besar, okay, so you will approach the activity jugalah, okay, approach the activity juga. Alright. Okay, the next one we will look into the chemical equilibrium electrolyte effect. Okay, dah saya dah discuss tadi tentang common ion effect dengan non-common ion effect. Bila kita ada common ion effect, dia akan decrease the solubility of the targeted components. Meanwhile, if we introduce electrolyte which contain no common ion effect, dia akan increase the solubility lah. Okay, so saya dah explain ni tadi. Okay, kalau kita tengok sini K something tartrate, so maybe KC lah, I put over there. So if we introduce common ion effect into this particular thing, dia tak akan dissociate lah. Okay, tapi kalau kata kita put anything else as the electrolyte, dia akan improve the solubility. Okay, if you look over here, the solubility lah increasing. Okay, so macam ni you tengok graf ni, mungkin yang lama dah tak tengok graf, macam ni lah tengok dia. So kalau kita tengok sini KCl, bila kita bertambah concentration of KCl ni, lagi banyak common ion effect, lagi rendah solubility potassium hydrogen tartrate. Ini common ion effect. Tapi magnesium sulfate ni, kalau you tambah, sebab dia tak ada common ion effect, dia tambah effect of the ion strength of the solution, dia akan tambah the solubility of the targeted compound ni lah, potassium hydrogen tartrate. Okay, now let's look into thermodynamic inspiration. I don't want to make a headache to you guys, so I believe you guys already learned a lot of it during the physical chemistry. But I want to frankly, to be honest with you guys, I'm also not very good in the physical chemistry myself. Okay, so let's learn together. Right, so in the thermodynamic inspiration, okay, before we go into detail, okay, I want to make some refreshment about enthalpy and entropy. Okay, the enthalpy refer to the change of heat lah in the system, change of heat. Okay, for example, from this to this, how many heat. Okay, but for the entropy, the disorderness. Okay, the disorderness, for example, the particle in the solid become this. Okay, become this. Okay, measure the disorderness lah. Okay, so that is for the entropy. Okay, for the enthalpy, we need to calculate the heat, okay, from here to here. That's why you can see the diagram like this, right? Okay, right. Okay, kalau you tanya saya apa itu S, I'm not really sure lah kenapa heat, H for heat, I understand lah. S, I'm not really sure, mungkin lah nama orang yang cari entropy, nama dia Samsudin ke, so letak nama S depan tu lah, probably lah. Cuba lah you check, I believe so lah. Okay, kadang-kadang dalam bahasa kimia ni, itulah macam-macam keluar, Rock's law lah, Triton law lah, Truton law lah. Okay, so jangan tanya saya kenapa je letak S, I'm not really sure how. Okay, I'm not really sure why. Okay, right, so sekarang kita kena tahulah, okay, kenapa kita perlukan, not kenapa kita perlukan, why the thermodynamic is related to spiration lah. Okay, spiration actually involve the missing of species of phases lah. Selalunya kita akan try to make sure that particular species dia tak static on that one place lah. Sebab kita nak spread them, kita kena introduce another phases lah. So kita deep missing the species, ataupun kita daripada satu phase tu kita wujudkan dua phase. Contohnya water, one phase of liquid, kita create the vapor phase of water. That's example. So the thermodynamic sense resulting in a decrease of the total entropy lah, in the total entropy. Right, So one way of accomplishing the separation is to create more phases. Macam saya cakap tadi, kalau kita nak tambah separation ataupun kita nak improve separation, and what we can do is we create more phases. Okay, sama ada by contohnya kita introduce the temperature ataupun kita introduce another chemical, okay, another type of solvent which is immersible. Okay, we can do that. Okay, right. So the Gibbs phase rule give for the degree of freedom G for a system of B phases and C components. So G refer to degree of freedom lah. Ada yang guna F so kalau you cari ada yang guna F, so nothing wrong with that. Kalau you guna F pun tak apa, tak ada masalah. So saya akan faham. B refer kepada berapa banyak phase yang you ada, contohnya liquid ataupun water, ataupun you ada dua. C tengoklah komponen you apa dia. Okay, kalau komponen you hanya ada satu, contohnya you nak fokus kepada water saja, yes. Tapi kalau kata contohnya you ada compound A and compound B, so you ada dua components. Okay, so if you look over here, G equal to C plus 2 minus B, ataupun you boleh jumpa juga kadang orang tulis G equal to C minus B. Okay, ada juga tak kisah, asalkan lebih kurang, bukan not lebih kurang lah, at the end it's refer to the same equation, derive to get the same equation, it should be fine. Okay, if you look over here, as G increase, this mean that the entropy increase as well lah. So as G decrease, okay, it reduce the total entropy. Okay, right. A new phase can be created by adding a new component. Kita boleh tambah adsorption, desorption, or we can put extraction. Okay, ataupun kita boleh tambah the energy lah, adding or removing energy through heat, distillation, crystallization. Right, so it can create, okay, an equilibrium which will initiate the separation lah, or chemical reaction. Okay, right, and now let's look on the Gibbs free energy. Okay, a thermodynamic potential that measure the maximum or reversible work that may be performed by thermodynamic system at constant temperature and pressure. Okay, untuk Gibbs free energy ni terpakai bila the separation system we made lah, kita buat dekat constant temperature and pressure. Agak-agak sistem apa yang sebenarnya separation ni yang dekat constant temperature and pressure. Maksudnya kita tak tambah temperature, kita tak tambah pressure in that particular separation system. Okay, alright. Kalau kata contoh yang saya boleh bagi adalah liquid extraction lah, liquid extraction, kita tak apply temperature and kita tak apply pressure, but it doesn't mean that bila kita tak apply temperature and pressure there is no new formation of temperature, there is no new formation of pressure. Boleh berlaku boleh berlaku. Okay, so kalau kita tengok sini, Gibbs free energy change equal to 0 kalau dekat equilibrium lah. Contohnya nothing happen lah, orang kata nothing happen. Contohnya bila you nak analyze H2O, nak analyze alcohol in the H2O, but you adding more H2O, so agak-agak ada separation tak berlaku, so tak ada separation, so it's already equilibrium, nothing happen. Okay, so Gibbs free energy dia akan jadi kosong. Okay, so kalau sini perubahan G, okay, the change of G, Gibbs free energy, is depends on the enthalpy, the change of enthalpy and the change of entropy. The equation of it is change of energy equal to enthalpy change minus the change of entropy multiplied by temperature. If you look over here that G is negative where the reaction is spontaneous and G is positive where reaction is non-spontaneous lah. Okay, right. Selalunya kita boleh related dengan endothermic dengan exothermic lah. Exothermic kan, endothermic dan juga exothermic. Right. So if the reaction is exothermic lah kan, selalunya exothermic is already negative lah, you punya enthalpy kan. So kalau negatif, tolak lagi something, dia akan jadi negatif, confirm dia adalah spontaneous. Okay, and tu kita, yang ni saya bincang daripada sudut dia endo atau exo. Kalau dia endo dia adalah positif, so dia akan jadi positif, so it's no spontaneous lah. Okay, selalunya kalau kata in chemical reaction, kalau kata selalunya lah dia adalah non spontaneous, selalunya dia akan back forward lah, dia akan bertambah di sebelah kiri lah selalunya kan, the reaction punya chemical formula. Tapi kalau kata selalunya dia adalah spontaneous, selalunya dia akan ke arah produk lah. Okay, so kalau kita tengok dekat sini juga, based on its, kalau kata the enthalpy is exothermic or enthalpy is endothermic. Okay, let's say lah, okay, kita tengok pada entropy alone, kalau sekiranya the disorderness itu sangat kecil, okay, maksudnya disorderness tu sangat kecil ataupun negatif, okay, dia akan jadi positif. Maksudnya daripada gas, okay, dia jadi liquid, jadi solid. Ataupun okay, you dah banyak dah partikel dekat between phases ni, tiba-tiba je tak mau pergi dekat another phase, dia tak nak pergi ke another phase, dia berkumpul kat sini, dia makin rapat. Okay, dia makin rapat, instead of dia pergi to another phase, dia makin rapat. So dia akan jadi inilah non-spontaneous. Sebab apa? Bila dia entropi ni, bila dia jadi lagi rapat, dia tak mau berpisah, dia tak mau separate, dia lagi rapat, so the value become negative. So the total G, okay, minus T, you darab dengan negatif, dia akan jadi positif kan. So dia akan jadi lagi non-spontaneous. So kalau you rasa you nak pilih spontaneous ke non-spontaneous untuk you punya reaction, so kita akan pilih selalunya adalah spontaneous lah. Kita akan cuba dapatkan the total change of Gibbs free energy ni less than 0 ataupun negative. It mean that the separation occur, the particle start to undistributed to another phase. Itu sebenarnya kita punya target lah, selalunya itu yang berlaku. Okay, how Gibbs is related to the distribution coefficient. Kita sebenarnya boleh kira, right, the Gibbs energy based on this lah, negative R T ln Kp. Okay, Kp equal to this one lah. Okay, at the end you boleh calculate ni lah, Kp sama dengan G naught over RT negative, and then you shift ln lah, shift ln dia apa dalam calculator, tak ingat lah, check sekejap, use my calculator. Okay, shift ln adalah E lah, E. Okay, then you aku dapat Kp lah. Okay, kalau you dah kira G ni macam mana, dan daripada tu alone, okay, kalau kata you tak ada concentration, okay, you boleh kira Kp juga you boleh kira partition coefficient tanpa masalah. Okay, again, okay, you boleh kira ni Kp, okay, dengan you cari the Gibbs free energy ni berapa, and then you divide by the R is the constant for the particular gas lah, if I'm not mistaken, and you divide by that temperature. Okay, and then you calculate, use ln lah, you will dapat balik Kp ni. Okay, again, Gibbs energy only apply where the pressure and temperature is constant, where you don't apply different temperature, you don't apply different pressure, ataupun kadang-kadang bila you apply temperature, pressure is suddenly raising, right? So the pressure is not constant automatically. So example lah, bila contoh you guna distillation, okay, of course you play around with the temperature, of course you will play around with the pressure, then you cannot use, you can no longer use the Gibbs free energy equation. You need to use another equation by another person punya lah. Yang ni nama orang dia adalah Clausius Clapeyron kan, Clausius Clapeyron. Okay, again here you tak perlu susah payah untuk hafal. Kalau kata soalan tu bagi, kita akan bagilah the equation at the back. So if you look over here, okay, log P equal to negative H over divide by 2.3 RT plus constant lah. Okay, so log P ni sebenarnya sama dengan log Kp lah, log Kp, okay, it's the same, right? So this how you can utilize it lah, okay, for per use, right? So if in this question where P is vapor pressure at known temperature, H is the enthalpy of evaporation if the substance is liquid, or enthalpy of sublimation if it's solid, R is the ideal gas law constant, and T is the temperature in Kelvin. So you need to cancel out the unit, okay, so you can calculate them, but I'm not really sure if it's involved in the calculation later on, or it involved in the test or the final, but you need to understand. Okay, usually we'll give you the right information, you just need to substitute inside of the equation. So you need to practice using calculator lah. Later on you need to practice using calculator. What is the log, what is the shift log, what is the ln, what is the shift ln. Okay, you need to try using the calculator. I believe you already learned this so much during the physical chemistry. Right, so if for example the equation over here, okay, doesn't give you information about the enthalpy of the change of H right here. So the change of enthalpy, you can use the Thornton's rule. Okay, let's say the question is a little bit tricky, doesn't provide you with the change of H, so you can use the Thornton's rule. What is actually mentioned by Thornton's rule? Thornton's rule mentioned that entropy of vaporization is almost the same value. It's about 85 to 88 joule per kilo per mole for various kind of liquid at their boiling point. The entropy of vaporization is defined as the ratio between the enthalpy of vaporization mole and normal. Okay, it's about the same lah. So as we know that previously, right, in this particular equation, at the equilibrium that the G equal to 0, okay, G to 0, it means that the system is already at equilibrium, so we want only to focus on the enthalpy of vaporization. Okay, so you can have that at the original, the G is equal to the change of heat minus T over S, right? So let's say if G equal to 0, you get H equal to the change of S, so H over T equal to S lah. Okay, so the change of vaporization, okay, you can calculate by multiple the theta H S T lah. Okay, so the common entropy for the liquid lah. Not I saying that all the liquid they have the same liquid entropy value as the vaporization. No, I'm not saying that, but most of the liquid, not most lah, majority of the liquid, but not all of them. Majority of the liquid, they have in from 85 to 88 S value, or yes, over here, right? So you can use this. Okay, so you can calculate the change of heat at vaporization, and then you multiply by the boiling point of that particular solvent, and then you can get the J per mole lah. So make sure that you convert, you need to calculate in Kelvin lah. And then of course, if for example if you use this particular unit calorie K per mole, you need to use 21 lah if you using this one lah. Okay, so the unit is K 1 mole. Okay, this we use calorie lah, okay, if we use calorie K per K per mole lah. Okay, if you use J joule per K per mole, then you need to use this, right? So you can use to estimate the H of vaporization lah. So you can substitute in this particular equation. Right, that's it about the in the thermodynamic. Okay, and then the next thing about the phase rule. Okay, now let's learn about phase rule. Okay, before this we already learned about a few rules that we want to look at, either how it's related to the partition coefficient, how it's related to separation. Okay, so what kind of the equation we should apply, okay, to study the the KP, to calculate the KP value. Okay, if for example we want to calculate using fixed temperature and pressure, we can use the Gibbs free energy. If for example the system is not at constant temperature and pressure, we can use the Trotter's law and also the Clausius-Clapeyron rule. Okay, so now we want to learn about the phase rule. Okay, phase rule is that we want to predict the number of stable phases lah, okay, that may exist in equilibrium for a particular system. Okay, so the phase rule, we want to know that, okay, how many variables that we can play around, okay, in that particular system. Okay, for example, kalau kata lagi banyak variable that you can play around in that particular system, the phase is stable. Okay, contohnya kalau kata kat sini you boleh main temperature and pressure banyak. Okay, so maksudnya kat phase ni you boleh play around temperature and pressure dekat certain value lah, dia ada limitnya. Okay, so it mean that it's stable. Okay, contohnya kalau kat sini mungkin dia tak stable lah, maksudnya as the degree of freedom dia sikit kalau kata compare dekat sini. Okay, later on I will discuss on you, we'll discuss, okay, macam mana kita nak tahu dia stable ke tak. Okay, so dekat sini kita ada equation lah untuk how we can calculate either the phase is stable or not. So we can calculate the degree of freedom, G equal to C minus B plus 2. Okay, sometimes you will found the equation as F equal to C minus B plus 2, or you can found C minus B plus 2. Okay, F for freedom, P for phase. So it doesn't matter because it's the same thing lah. Okay, so if you look over here, that kenapa pentingnya phase rule ni, kenapa pentingnya extraction dekat stable phase, sebab kita nak tahu apa yang kita boleh manipulasi in our variable, ataupun sejauh mana kita boleh manipulate our variable untuk untuk our punya separation punya system. Okay, for example, let's say you want to analyze compound, only one compound dekat water, dalam air. So contohnya dekat point A ni, okay, the component is komponen je satu sajalah, sebab kita ada satu komponen sahaja, dan B ni kita ada berapa? Kita ada satu saja. B adalah phase, so kita cair kita adalah satu saja. Phase kita adalah cair, 1 minus 1 equal to 0. Okay, 1 minus 1 equal to 0 plus 2 lah. So you get 2 lah, plus 2. So kalau kita tengok sini, apa yang dimaksudkan dengan plus 2, it means that you have two variables that you can play around. Two variables in this particular system that you can play around. For example, kat A ni, at given pressure, okay, kat this pressure, okay, you can play around suhu dia. Okay, you boleh play around suhu dia. Okay, ataupun dekat A ni, you boleh fix the suhu, you can play around with the pressure. Okay, so you ada berapa yang boleh play around? You boleh play around dua variable. So that's why the degree of freedom for A is 2. So it means that you have the freedom that you want to try the variable. Okay, ada dua kat situ. Okay, but it doesn't mean that you can play around up to everything lah. Dia ada limit. Contohnya bila sampai sini you dah masuk another phase ataupun another limitation. Okay, that is for example for that particular thing lah. Okay, so contoh yang lain dekat B lah. B, okay, you ada satu komponen, sebab kita satu compound saja kita nak analyze. Mana B ada berapa phase? B kat sini kita kena letak dua phase lah, sebab kita ada cair, kita ada warp, itu we have liquid, we also have the vapor. 1 minus B. So if at B 1, the component is 1 minus B berapa tadi? Phase is 2 plus 2. So 1 minus 2 negative 1 plus 2, you have only 1 lah. Okay, you only have one freedom that you can change. For example here, at this particular line lah, okay, you can only either adjust temperature or pressure only. You can adjust a lot of things. For example, you want to stick in this particular line. Okay, so they must be dependent to each other lah. Okay, right? So it can still move over here, but you need to, for example, at this particular pressure, you need to apply this temperature, okay, or at this particular pressure you need to apply this temperature. So you only have one independent variable, okay. So you ada satu saja you boleh ubah, tapi yang lain tu nak tak nak kena follow. Itu dimasukkan dengan itulah, okay. Contohnya kalau kata you want to stick dengan ni, nak tak nak kalau kata you nak apply suhu sini, whatever you do, you need to accept that this is the pressure that you will counter, okay. That's the pressure that you will counter lah, okay. Compare tu dengan ini, kalau kata you nak apply suhu sini boleh, nak main dengan temperature pun boleh, tak ada masalah. Tapi kat sini ada limitation, okay. Dekat kawasan ni, kalau kata satu tu you ubah, lagi satu tu you tak boleh buat apa-apa, okay. That's what it mean by that, okay. So now let's look at the triple point, okay. Triple point where you have all the three faces, okay. So at the triple point, for example here, component you number still 1, okay, and the B faces you have 3 lah, 1, 2 and 3. 1 minus 3 you got negative 2 lah, negative 2 plus 2, and then is equal to 0 lah. So it means that nothing that you can do over here. You cannot change pressure, you cannot change, because you only have one triple point, okay. You cannot have 2 point, okay. You cannot move anything else. It should be stick over there only, okay. Tak boleh ubah apa-apa, okay. So the thing that I want to stress over here, that it doesn't mean that as the number of the phases as the number of freedom, okay, increase, that it doesn't mean that is the best phase for you, okay. It doesn't mean that is the best phase for you, not necessarily, not necessarily. It just mean that you can have more variable to play around, okay, to improve the extraction, but not necessarily that is the best. Who knows, maybe at the triple point the extraction is the best, you get the optimum extraction over there, okay. So the phase rule only want to describe to us that is the most stable phases that you can play around, okay. For example, with the pressure you want to play around, with temperature you want to play around, with the volume you want to play around, with the concentration of the reactant, for example. That's what it's mean by phase rule. Doesn't mean that as the number of degree of freedom is increasing, the spreadsheet is better, okay. It's better for flexibility, okay, but not necessarily you get the best separation at that particular phase, okay. Right, when the number of the degree of freedom increase lah, itu yang saya masukkan. Kalau tak faham nanti boleh tanya balik, right. Okay, here is another example of phase rule lah. Here is the example of phase rule when we have the binary component lah. Binary components, maksudnya kita ada dua components lah yang kita nak extract kat sini. How they affect each other. So we have A component and B component lah, okay. So dekat sini sama, equation kita pakai G equal to C minus B plus 2, okay. If you look over here, for example at X, okay, how many phase you have? You have 1 lah, ataupun B lah kat sini. You get confused, okay. So how many component you have? Component you ada 2 lah, so 2 lah. Kalau kata dekat X ni adalah C kita, komponen kita ada 2, minus berapa B kita? Phase kita ada 1, so plus 2, you get 2 minus 1, you get 3 lah, you get 3. Dekat sini ada 3, so you boleh ada suhu, you boleh ada fraction, okay, if you want to manipulate during the separation, and then you can also have the pressure lah. So the Z, so you have pressure over there. So a lot of thing that you can do, okay. Let's say at point Y, okay, you have components still 2, phase you have 2 lah. You have gas phase, we calculate as one phase, not calculate by 2 phase, kita kira anggap je sebagai satu phase. Then here another phase lah, so you get 2 minus 2 plus 2, okay, you get G equal to 2. So you only have 2 components that you can play around lah. Okay, so the one must follow the other. For example, if you change the temperature, you need to willing to accept whatever fraction, okay, you need to that is determined over there. But for example, you use this particular fraction of mole, then you need to accept whatever value of the temperature given to you during the experiment or during the separation. So that's how actually we calculate the phase rule in case of binary punya system. Binary component lah, 2 component lah, right? Okay, yang terakhir adalah Rod's law. Okay, Rod's law ni sebab sepatutnya kita discuss Rod's law ni boleh discuss sebenarnya dekat sini after Thornton's law, sebab ataupun kita boleh sebenarnya boleh explain dekat Clapeyron equation, sebab contohnya kita nak kira pressure is not given kan. So apa yang kita boleh buat, kita boleh apply sebenarnya Rod's law ni, okay, untuk calculate the pressure or partial pressure lah, okay. So tapi saya terangkan last Rod's law ni sebab dia juga berkaitan dengan phase rule. Okay, dalam phase rule ni kadang-kadang kita ada a fraction of vapor pressure bila the compound is not pure lah, maksudnya contohnya okay, kat sini lah saya nak explain. Okay, contohnya you want to the vapor pressure, okay, in Rod's law dia kata kat sini seandainya, okay, nak kata kat sini seandainya you introduce another components inside here, okay, the vapor pressure will change, okay, dia akan berubah. Contohnya you tambah garam cukup lah, you tambah garam dekat dalam this particular solution, kita ambil lah H2O, the vapor pressure dia akan berubah. Okay, so dekat sini dia kata kat sini the partial vapor pressure of each component of an ideal mixture of liquid is equal to vapor pressure of the pure components multiplied by its mole fraction in the mixture. So right, okay, contohnya lah kat sini apa yang dimaksudkan, okay, vapor pressure contohnya without anything at pure, okay, for H2O you dapat contohnya 25 torr pressure. Okay, so let's say you want to determine, okay, vapor pressure of the partial vapor pressure, okay, of the system yang you dah introduce. Contohnya macam you ada compound ke, okay, you nak kira the partial vapor pressure, okay, then what you can do that, okay, you can calculate the mole fraction, okay, for example, okay, the mole of H2O, okay, over mole of H2O plus, contohnya kita letak sini garam lah, NaCl, okay, you multiple by this vapor pressure lah, okay, this yang pure punya vapor pressure, contohnya 25 torr ni. So bila you darab, you akan dapat the vapor pressure of this particular H2O which is not pure lah, which is a mixture with this particular salt. Okay, this is how you apply the Rod's law. So here, if you look over here, PA is the pressure of solvent A. Okay, so here is the solvent A lah. Okay, SA is the mole fraction of solvent A in a solution lah. So SA is actually equal to ni lah, yang tadi saya bagi ni. Ini, kenapa saya tulis jauh sangat, sorry. Yang ini adalah SA ni. So PA is the vapor pressure, PA naught ni adalah vapor pressure of pure solvent. Okay, at the same temperature, make sure they at the same temperature. You cannot calculate the Rod's law if you using different temperature setting. Okay, contohnya you kira pure punya vapor pressure dekat 30 degree, tapi bila dekat yang mixture punya tu you want you apply at contohnya dekat 25 degree, tak adil lah. Okay, kena compare yang sama. So yang ni ada class activity. 50 gram of glucose dissolved in 500 ml of water at 24 degrees Celsius. What is the vapor pressure of the solution? Given that the pressure of water is 30 torr at 24 degrees Celsius and density of the water is 1 gram per ml, blah 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 blah. So yang ini saya tinggalkan untuk class activity. So kita akan discuss lah dalam next week. Okay. Untuk next week, saya rasa saya tak akan buat quiz hari Selasa sebab dia Selasa pagi tu kita ada kelas kan, nanti you guys hilang fokus. So saya akan setting hari Khamis lah, hari Khamis daripada pukul 2 sampai pukul 7 malam. You guys boleh masuk anytime, okay, untuk menjawab quiz. Ataupun saya buat awal lagi lah, pukul 1 tengah hari tak boleh. So jangan masuk semua serentak semua pukul 1, korang masuk lah, beza-beza sikit. Right, thank you so much.